Let's work on a problem that involves Newton's method. So Newton's method is a way to estimate the zeros of a differentiable function. And let's just remind ourselves of what it is. It's given to us by this recursive definition. Recursive meaning that it's going to start with a value, and then that value is going to lead us to another value. And that value is going to lead us to another value. And it's going to generate this sequence of x values. And those x values are going to zoom in on the zero. So as we keep doing this over and over again, it's going to generate a sequence that converges to what we're looking for. So let's just write down this recursive definition because we're going to use it. In fact, let me write it down in the order that I like to think of it. Given an x value, I can take it and I can subtract the ratio of the function at the x value compared to the derivative at the x value. And this is how I get my next value. So we're going to use this definition to generate 4 iterations of Newton's method to estimate the positive root for this function. So let me zoom in here to give ourselves an idea of what's happening. We are interested in the function x squared minus 2. So it's going to look something like this, and this right here is the 0 that we're looking for. Now, our initial guess, our first x value that we're going to use is x is equal to 1. So x is equal to 1 is somewhere right here. That's going to be our first guess. And now let's go through the process of Newton's method. So our first guess is 1. Our next guess will be given to us by Newton's method. So our function is x squared minus 2. The derivative is 2x. So my next x value in the sequence will be given to me by my first guess, 1 minus f at 1 over f prime at 1. And that is 1 minus a minus 1 over a 2, or a 1.5. So what we're doing is we're walking along the tangent line. And our next guess is 1.5. So that's also not the right root. Let's do another iteration of this. So our second value will be given by the first value minus the function at the first value over the derivative at the first value. So our second guess will be given by 1.5 minus f at 1.5 over f prime at 1.5. Mm-hmm. Now I'll skip the details. All you have to do is evaluate your function at 1.5 and your derivative at 1.5, run through this equation, and your second value is, we're going to have to approximate 1.41667. So what we just did there was we drew the tangent line at our next guess, and then found the 0 of the tangent line, and it got us closer to the actual root. And we'll just continue in this manner. Our third x value will be given by the second x value minus the function at the second x value over the derivative at the second x value. So this will be 1.41667 minus f at 1.41667 over f prime at 1.41667. So skipping the algebra, I'll trust that you can do this. Your third x value is 1.414216. So if I can zoom in a lot now, I'll have to clear off the board. we now took that guess, looked at its tangent line, and it got us even a little bit closer. So we're really just zooming in on that 0. And let's look at one more. So in fact, how many times have we done Newton's method? We went from x0 to x1 to x2 to x3. So we've done it once, twice, 3 times. We'll do it one more time to get to 4 iterations. So x4 will be given by x3 minus f at x3 divided by f prime at x3. This will be 1.414216, right? It's this number minus your derivative at that point, or sorry, minus your function at that point divided by your derivative at that point. All right, if we do this one more time, we find that x4 is 1.414214. So notice as we keep doing this, our first change moved us from 1 to 1.5. So it moved us quite a bit. But then we moved from 1.5 to 1.4167, and then 1.4167 to 1.414216. So we're starting to zoom in on this 0 right here. In fact, you can think of this as solving for the 0, or rather estimating the 0 of this function. And the 0 of this function comes from x being the square root of 2. At least the positive one is. So you can think of this sequence of x values, x0, x1, x2, x3, and x4, as being approximations to the square root of 2. And you can plug this into your calculator and you get something that's very, very close to that.